Welcome to EcoCommons, the platform of choice for analyzing and modeling ecological and environmental challenges. My name is Emilia Decker, and in this module I will show you how you can manipulate and analyze data in R and turn data like this into something more readable like this. All using a free high-performance computer in the cloud, so you don't even have to burden your own personal computer. Here at EcoCommons, we empower students, researchers, and decision-makers to protect and restore the planet by drawing on the immense expertise of our partners, collaborators, and top scientists. We provide access to ecological and environmental data, robust scientific workflows, and digital infrastructure at your fingertips. You can learn how to quickly turn noisy data into high-quality results in an easy-to-use point-and-click environment, or brush up on your coding skills. If you are an early career researcher, student, educator, or policy decision maker with keen interest in ecological modeling, EcoCommons is for you. EcoCommons will help you to spend less time data wrangling and configuring models and more time on restoring and protecting the planet. So let's have a look how we can manipulate and analyze data in the R environment on EcoCommons.
Before we begin, let's open RStudio on EcoCommons. Click on Analysis Hub and then Coding Cloud. Press Launch Notebook Server and then choose the EcoCommons R environment, which includes RStudio with the most popular packages. Press Open to start a Jupyter Notebook server and click on the RStudio icon to launch the RStudio server. To open a new R script, click on the white square with the green circle in the top left corner and choose New Script. Let's begin by setting up our working directory. For that, type setwd for setting working directory, and in brackets, type in the path of your working directory. If you're working in Coding Cloud of EcoCommons, we recommend to set up your working directory in your workspace. Run the code by pressing Run, or Command Return if you're on a Mac, or Control Enter if you're on a Windows. Next, let's load the Tidyverse R package we are using for this module. Tidyverse is pre-installed on EcoCommons, so you just need to load it. For that, type library and in brackets Tidyverse. Tidyverse is an umbrella package which includes many other R packages, and in this module we will mainly use ggplot2 and dplyr. Now that we have loaded the package, let's create some folders where we can store different types of data. To create a folder, type dir.create and in brackets the name of the folder. Let's create a folder called data_raw, where we can store our raw data. Next, let's create a folder where we are going to store the process data and call the folder data. The last folder we want to create is called fig, for figures, where we are going to store our figures that we will create in the next module. Highlight the code and then press Run or Command Return for Mac or Control Enter for Windows. You can see in your file structure in the bottom right corner that you now have created 3 folders. Now let's download the data that we are going to use in this module today. We are going to use the function download.file. The first argument of this function is the URL. Pause the video if you need to make sure you get the right file. We also need to tell the function where the file should be stored and what its name is. We can do this by using the argument dest_file. Type dest_file equals to, and then in quotation marks, data raw, which means the data will be saved in the data raw folder, /forward, and then we call the file portal_data_joined.csv. Run the code by either pressing Command Return for a Mac or Control Enter for Windows. In your data raw folder, you can see that we have now downloaded the CSV file. Now that we have downloaded our data, let's read it into and put it in an object in R. Let's call the object surveys. And to read the CSV file, we're going to use the function read_CSV. It's very important to use the underscore and not the dot, because the underscore reads the file a little bit different than the read.csv function. In brackets, type the pathway where your data sits. In our case, it's data_raw/forward portal_data_joined.csv. Run your code by either pressing Command Return or Control Enter. Now let's view the data using the function view. Type view and in brackets surveys. Now run the code. Your data will be open in a new window, and we can see that surveys contains 13 columns and over 34,000 observations or rows. We can see that there are a few NAs or no values. Then we can also see the names of the columns. Now let's pretend we don't want to see all the columns, but we only want to see specific ones, like plot ID, species ID, and weight. For that, we can use a function which is called select. The first argument in the function select is the data frame, in our case, surveys, followed by the columns that you want to choose. In our case, plot ID, species ID, and weight. Press Command Return or Control Enter to run the code. R gives us now the first 10 rows and the 3 columns that we chose. Now let's select all columns except for record ID and species ID. Type select, and then the first argument is our dataset again, and then put a minus in front of the columns that you want to exclude. In our case, minus record ID and minus species ID. Run your code. And you can see I did a mistake here. I had a typo, which threw me that error. So once I clean up my error and run the code again, you can see now that it will give me the first 10 rows and 11 columns, because we excluded 2. But what if we want to select specific rows with a condition? For example, filter for rows in which the year is 1995. For that we use the function filter, and similar to select, the first argument is our dataset surveys, followed by the condition, in this case, the year which is equal to 1995. And as you can see here, we have filtered for all the rows in which the year is 1995. We can also select columns and filter for rows at the same time. For example, we can look for species with the weight smaller than 5 and select columns, species ID, sex, and weight. You have three options. The first one is called an intermediate step, where you create a temporary data frame. With this option, we create a new object. Let's call it Surveys2. Then we filter for all the species that have a weight smaller than 5. Now we can create a new object. Let's call it Surveys Small. And using the Surveys2 data frame that we just created, we can select the columns Species ID, Sex and Weight. Looking at our Surveys Small data, we can see that we now have 3 columns and the weight is smaller than 5. This approach might be handy, but you will clutter your work environment a lot. So let's have a look at the second approach, which is called a nested function. With the nested function, one function sits within the other one. So let's create an object called Surveys Small number 2. We assign it select, and then within the function select, we're gonna use the filter function. Type select, and then in brackets filter, then another pair of brackets, and here we filter for all the species that have a weight smaller than 5. Behind the first brackets, put a comma, and now select the columns Species ID, Sex and Weight. Once you hit Run, you can see that we have now created the same object as before. The third and last option is a pipe operator, which is a percentage sign, followed by a greater than sign, followed by another percentage sign. The shortcut for that is Command Shift and M. The pipe operator can also be read as and then. For example, here we have surveys. This means go get the data and then filter for all the species with a smaller weight than 5, and then select the columns Species ID, Sex and Weight. We can also create an object using the pipe operator. For example, let's create an object called Surveys Small number 3. And similar to the code above, we assign it surveys, and then, using the pipe operator, filter for the species with the weight smaller than 5, and then select the columns Species ID, Sex and Weight. And now, as you can see, we have created another object similar to the first two. Now let's do a little challenge. Can you find how you have to subset the survey's data to include animals collected before 1995 and have only the columns year, sex and weight? Pause the video if you want to give it a try. Otherwise, keep watching. To solve this challenge, we first need surveys, our data. So let's type surveys, pipe operator, and then filter for all the years that are smaller than 1995, pipe operator, and then let's select the columns year, sex, and weight. Run your code, and as you can see here, we have now selected these 3 columns and the year that is smaller than 1995. Next, I would like to show you how to create one column based on another one with the function mutate. The weight column in our dataset is in grams, so let's create a new column in kilograms. Type surveys, pipe operator, and then we will use the function mutate, and in brackets we will give the column that we are creating a name, in our case weight underscore kilograms, and say it is based on the weight column, and we can use mathematical operations to create and divide it by 1,000. So as you can see, we have now created a 14th column called weight underscore kilograms, which is based on the weight of the previous column. We can also create a second column based on the first column that we created. Type surveys, type operator, mutate. Let's create a column that is called weight underscore kilograms, which is based off of the column weight divided by 1,000. And then comma. Let's create another column called weight underscore lb for pound, which is based on the kilogram column that we've just created, times 2.2. And let's look at the first 6 rows instead of the first 10 rows, using the function head. Once you run the code, you can see that we're now looking at the first 6 rows and that we have created 15 columns, one called kilogram and one called weight underscore lb. But we also have a lot of NAs, which is because the column weight also has a lot of NAs. Now let's get rid of those NAs, or non-number. To remove NAs, let's type surveys, pipe operator, filter, and then in brackets exclamation mark, and that exclamation mark negates anything that you type afterwards, and we will type is NA. So this means give me everything that is not an NA in the column weight, and then we mutate. Again, we will create a column called weight underscore kilograms based on the column weight divided by 1,000. And then we will look at the first 6 rows by using the function head. And now as you can see, the columns weight and weight underscore kilograms don't have NAs anymore. But what if you want to exclude or remove all the NAs in your whole dataset? Well, for that we can use the function that is called NA omit. Type na.omit and then in brackets surveys. Hit run, and now you can see that we have our surveys without any missing data. Let's do another challenge. Try to create a new data frame without any NAs that is called surveys underscore hindfoot underscore centimeters. This data frame should only contain columns species ID and hindfoot underscore length underscore centimeters, which is converted from the column hindfoot underscore length. This column is in millimeters. Further, the new created column hindfoot underscore length underscore centimeters should only contain values that are less than 3. If you want to give it a try, pause the video. Otherwise, let's continue. To solve this challenge, let's create the object first. Let's type surveys underscore hindfoot underscore centimeters. Then we want to get rid of the NAs first. Type in na.omit and in brackets surveys. Use the pipe operator, and in the next line, let's mutate the columns. We want to create the column hindfoot underscore length underscore centimeters, which is based on the hindfoot underscore length column. To get it in centimeters, we have to divide the column by 10. And then we want to filter this new created column for all the values that are smaller than 3. Type filter and in the brackets hindfoot length underscore centimeters smaller than 3. And then we want to select the columns. Type select and in brackets we type species ID hindfoot length centimeters. Run your code. And now let's look at the data frame that we just created. Press surveys hindfoot underscore centimeters, and as you can see, it contains 2 columns. Many data analysis tasks can be approached using the split, apply, combine method. Split the data into groups, apply some analysis to each group, and then combine the results. The key functions are group by and summarize, which are part of the dplyr package, which in turn is part of the tidyverse package. Group by collapses each group, and Summarise gives you the summary stats of that group. Let's look at one example. Say we would like to know the mean weight of each sex in our data. We type surveys, and then the pipe operator. Type in the function group by, and in brackets sex. This will group all the data by the sexes, male, female, and undetermined. Next, we want to summarize these groups. Type Summarise, and in brackets, we're going to create a new column, which is called mean underscore weight, and we want the mean of the column weight. So we type mean in brackets weight, and we want to make sure that we remove all NAs. So we type na.rm for remove equals true. Once we run the code, we can see that we have now a data frame with 3 sexes and the mean weight for each sex. We can also group multiple columns. For example, if we would like to know the average weight of species according to sex, we can type surveys, and then using the pipe operator, we type group by, and in brackets sex, comma, species ID. This will group the data according to sex and species ID. Now we want to summarize the average weight of these groups. So after the pipe operator, we write in the next line, Summarise, and in brackets, mean underscore weight. This is the name of the column that we are giving. This column is based on the mean weight of the existing column, weight. So we type mean underscore weight equals mean and in brackets weight, comma, na.rm for remove NAs equals true. Once you run your code, you can now see that we have females of a specific species and their average weight. If you would save this in an object, you can look for all the sexes of all the different species IDs and their weight. Let's remove the NAs before we run the code, just so we don't always have to write na.remove. Sometimes you will forget those things. So to remove the NAs in your data, type surveys, following by the pipe operator, and then filter exclamation point is .na, that means is not NA, and in brackets sex, comma, exclamation mark is .na, and in brackets weight. Make sure your brackets are closed in the proper spot. Once you've written that, use the pipe operator, and in the next line, we're gonna group our data again. Type group underscore by, and in brackets, sex, comma, species ID, and then pipe operator, and in the next line, summarize. It doesn't matter whether you write summarize with an S or with a Z, it is the same function, just whichever way you prefer. I write it with an S here. After summarize, type in brackets your column name, mean underscore weight, equals mean and in brackets weight. We don't have to write NA/RM anymore because we removed the NAs before. And as you can see, we will get the same data frame as before. We can also summarize multiple variables at a time. For example, if we want to know the mean and the minimum weight of each species or sex, type surveys, then the pipe operator, then NA omit and in brackets surveys, so we exclude all the NA values in the whole data frame, pipe operator, and then group by in brackets sex, comma, species, underscore ID, pipe operator, and then summarize, in brackets, let's call the column mean weight, which we derive from the column weight, equals mean, in brackets weight, comma, the next column we will call min underscore weight, which is the minimum, so min, and in brackets weight, pipe operator, and then let's rearrange the whole data frame according to the minimum weight in ascending order. So we use the function arrange. Now as you can see, in the data frame we arranged so that the minimum weights come first. If we want to arrange the data frame in descending order, we type DESC and put an extra bracket around min_weight. Running the code, you can see now that the highest minimum weight comes first. Let's say we want to count the number of observations. For example, the number of observations for each sex that was caught. We have two options to do this. The first option is to use group by and summarize as we did before. Type surveys and then type operator, group by, and we want to group by sex, then pipe operator, summarize, and in brackets the column name, sex count equals to n, which is the function for count, and have the brackets empty. Run the code, and you can see we will get a data frame which tells us how many times a specific sex was counted. The second option is to use the function count. To use the function count, type surveys, the pipe operator, and then count, and in brackets sex. You can see R is giving us the same data frame as before. We can also count a combination of factors, for example, sex and species ID. Type surveys, then the pipe operator, and then count, in brackets, sex, species. Run the code, and now you can see how many times, for example, the females of a specific species were counted. Let's arrange the data frame, first alphabetical, and second counts in descending order. Type surveys, then the pipe operator, then count, in brackets, sex, species, then the pipe operator, arrange, and then in brackets, species, DESC for descending, and in brackets, N for count. Run the code. As you can see, we have the first species starting with an A, and the counts in descending order. Let's do a couple of challenges. First, can you find out how many animals were caught in each plot type surveyed? Second, can you find the mean, min, and max hindfoot length for each species using species ID? And third, what was the heaviest animal measured in each year? Return the columns year, genus, species ID, and weight. Pause the video if you would like to give it a go. Otherwise, let's continue. Let's start with the first challenge. How many animals were caught in each plot type? Type surveys, then pipe operator, and then count, in brackets, plot underscore type. Once you run the code, you can see each plot type and how often it was counted, meaning how many animals were caught. For the second challenge, find the mean, min, and max of hindfoot length for each species using species ID. Type surveys, then the pipe operator, NA, omit in brackets surveys to make sure that we don't have any NAs in our dataset, then pipe operator, then group by in brackets species ID, then pipe operator, summarize, again either with an S or with a Z, and in brackets hind foot length mean, that's what we call the column, equals mean of, in brackets, hind foot underscore length. Behind the brackets put a comma, then type hind foot underscore min for minimum equals min in brackets hind foot length, another comma, and in the next line type hind foot underscore max equals max, and in brackets again hind foot underscore length. Running the code, we can see the first 10 rows of the species and with the mean, min, and max of hind foot length for each species. Now for the third challenge. Type surveys, then the pipe operator, then na.omit to get rid of all the NAs in the data frame, the pipe operator, then group by, and in brackets year, pipe operator, filter, and in brackets weight equals max weight to find the maximum weight in each year, with the pipe operator type select in brackets year, comma genus, comma species underscore ID, comma weight. Pipe operator, and then let's arrange the whole data frame by typing arrange and in brackets year. As you can see, we now can see in which year, which genus and species was the heaviest. For the last part of this module, we want to clean and export the data that we're going to use for the next module, where we will learn how to visualize our data. We want to extract the abundance of species through time. First, we want to extract the most common species. That means species that occur more than 49 times in our dataset. We will create a new object and call it species underscore counts. The first thing we want to do is get rid of all the NAs. So we type na.omit and in brackets surveys. Then the pipe operator, and in the next line we type count and in brackets species underscore ID, pipe operator, and then filter in brackets n for count bigger or equal to 50. Run the code. Now we have created the object species underscore counts. Looking at it, we can see which species occur more than 50 times in our data set. In the next step, we only want to keep the most common species. So let's create an object called surveys complete, which we will extract into a CSV file later on. First, we want to get rid of all the NAs. So let's type na.omit and in brackets surveys. Pipe operator, and then filter, species ID, and then percentage sign in percentage sign. And what it does, it tells R to go somewhere else, in this case species_counts data frame, and extract the species ID from there. Run your code. We have now created a data frame where we have species that occur at least 50 or more times. Now we want to export the data into a CSV file. To do that, we type the function write_CSV, and like in the beginning, it is important to use the underscore and not the write.csv. In brackets, we type surveys_complete, that's the data frame we want to use, followed by file equals, and here we write the name and the path we want the file to sit in. In our case, data, the data folder that we have created in the beginning, // surveys_complete.csv. Run your code. And now let's double check. Clicking on the data folder, we can see that the surveys_complete.csv file has been exported.
We are now at the end of our module manipulating and analyzing data in R using EcoCommons high-performance computer. Make sure to check out our YouTube channel for more videos and visit our homepage at ecocommons.org.au to find more training material, support articles, and R scripts. Once you sign up, you have access to the platform of choice for ecological and environmental modeling. And if you have done so, we would really appreciate it if you could send us some feedback so we know how to improve our platform to better meet your needs. Please consider sharing this platform with your peers if you think it can help them to speed up their research for impact. Otherwise, I see you in the next module, and thank you for watching.